Okay, so let's start. Okay, students. Okay, in the previous class, we had seen. Actually, we had started dynamic latches and registers. Okay, so and the basic thing that differentiate it from the static latches and registers is in its functionality, as these dynamic latches and registers are based on temporary storage of charge on capacitors. Okay, this is the basic thing. This is the basic thing of operation, and look at this. The diagram of a dynamic transmission gate edge trigger resistor. So here we have shown the capacitors. These are capacitive capacitors, and this is the first transmission gate. Okay, and second transmission gate, second parasitic capacitor. Okay, and node 1 voltage will be decided by the charge content of this parasitic capacitor C1, and similarly node 2 logic level will be decided by the charge content of this parasitic capacitor C2. Okay, and this is the way in which these dynamic circuits work. Okay, and we had seen this thing in previous class. So we will move further here, and okay, let's see the problem. So one of the problem that is related to the clock is when we are using clock and clock bar both in the circuit. Okay, then there could be a problem that when, because we know that these are not ideal signals. Okay, and generally from the clock we generate the clock bar signal. Okay, just you add an inverter in between. Okay, and you get this clock bar. Okay, so clock bar is derived from clock itself. So when clock is high, clock bar will be low, and vice versa. So look at here, if there is a delay that gets introduced in clock bar path, then there could be a situation when clock and clock bar both are 0 at the same time, which is not desirable at all. Look at here, for this time window, the value of clock is 0, and the value of clock bar is also 0. Okay, this is 0 and this is also 0, and this may pose a problem in the operation of the circuit, and this time window is called as 0-0 overlap as both clock signals are giving a 0-0 value. Okay, and after this time delay the clock bar becomes 1 as clock is 0. Okay, and because of this delay again we can have one more time window where both of the clock and clock bar values are 1, and this is called a 1-1 overlap between clock and clock bar. Okay, so these things are not desirable. We do not want this thing to happen, but actually these things do happen in the circuit. So the circuit should be robust enough to overcome these things that gets introduced in the clock signal. So let's see what problem it may cause. So if clock and clock bar both are 0, then what can happen? If clock and clock bar both are 0, let's say if clock is 0 and clock bar is also 0, and this is 0, this is also 0. So what happens that under this situation, this PMOS is on, this NMOS will be off, this PMOS is on because the 0 is being applied at the gate of this clock, this PMOS, and low voltage that is actually non enabling for this NMOS. So this is not working, this is off. Okay, this is off. So the signal, look, one transistor from each of these transmission gate is on, PMOS from here and PMOS from T2. So actually T1 and T2 both are on under this condition. They both are conducting. So T1 is also conducting, T2 is also conducting. So it means that a signal at the input side, that is D, will pass to node 1 and eventually it will pass to at node 2 and to the output, final output Q. Okay, so which contradicts the behavior of these resistors, which should be actually operating in MS, master slave mode. So when this is on, this should be off, and vice versa, but this is not happening like this. Okay, so whatever signal values at the input is available, that is directly passing to the output Q, which should not happen. Okay, so this will happen in when clock and clock bar both are 0. Okay, now when for the second time condition, when clock and clock bar both are 1, okay, for 1 time window, again this will be off. So this is on, this will be off, this will be on. Now in this condition, NMOS from T1 will be on and NMOS from T2 will also be on. So again T1 and T2 both are conducting, both are transparent, both are in transparent mode. Okay, and again this D will pass through T1 inverter, T2 and I3 inverter to Q. Again the data is transparent, is going without any hindrance to the final output Q, which is again undesirable. Okay, so for these small time periods, for this 0 0 overlap and 0 1 1 overlap, the circuit is completely transparent to the input signal and it passes to the output Q directly. Okay, which is not desirable, which we do not want this to happen. So these are the problems that are associated with the this 0 0 and 1 1 overlap. Okay, so during the 0 0 overlap period, we had just seen this, the NMOS of T1 and PMOS of T2 are simultaneously creating direct path for data to flow from D input of the resistor to the Q output. Okay, this is known as race condition. This is known as race condition. So it means that the output Q can change on the falling edge if the overlap period is large. Okay, if this overlap period is large, then it may happen that output may change at this falling edge of the clock signal. Okay, which is not desirable for a positive edge triggered resistor, because we want signal to get captured only when the clock signal is rising, that is only during this transition and not at this transition. Okay, but because of this effect, the output value may change during the falling edge of the clock signal. Okay, which we do not want. Okay, and similar things may happen for 1 1 overlap region also. Okay, so this condition may be avoided if we satisfy certain things. Just take care of these things. If we satisfy this condition, that is the overlap for 0 0, if it is the circuit is drawn, the clock signal is derived such that this 0 0 overlap is smaller than the delay of the first transmission gate, than the delay of the first inverter and the delay of second transmission gate. Okay, if this condition is satisfied, then the effect of this 0 0 overlap and one will not be affecting the performance of our circuit. Okay, that is, the undesirable change in the output value will not occur if this condition is satisfied. Okay, so take a note of this condition, that whenever there is a chance that a zero overlap may affect the performance of the circuit, may affect the functionality of the circuit, then try to design the circuit with this constraint, and then you may hope that the circuit will function uh, properly. Okay. Alright, so this is the case here. Just and next we will come to the next topic, which is C square MOS register. Okay, and this C square MOS is actually called as a clocked CMOS, a clocked CMOS. Okay, and the property is that these type of circuits will be insensitive to clock skew, or the problem that we had just seen, that was 0 0 and 1 1 overlap. Okay, these circuits are insensitive to these problems. Okay, so to overcome the previous problem, these type of resistors were proposed. Okay, were proposed. Okay, let me go to the full mode. Okay, so look at this circuit. It again consists of two stage. This is the master stage, okay, and this is the slave stage. So two stages, and this is the input D that is applied here, D input. Okay, and each of these stages consist of one PMOS for the input of clock in the first stage, and one NMOS for the input of clock bar. Okay, and in the slave stage we have one PMOS for clock bar input and one NMOS for clock. Okay, and apart from these, there is one more PMOS and NMOS which are there for the feeding of input signal in the master and slave stage both. Okay, so basically this is an inverter. This is a inverter. Okay, and this is also an inverter. So this type of structure is actually a CMOS inverter. But here, when you compare this to the static CMOS circuit, then you will find that there is an inclusion of extra this PMOS and this NMOS. Okay, and take a note that this is clock bar, and this is clock bar, and here it's skew. Okay, and this node is the output of this first stage, and also the input of second stage. Okay, and this is the parasitic capacitance CL1, the load capacitance for first stage, and this is the second stage load capacitance, and which is actually the final output Q. Okay, so now let us try to figure it out, the functioning of this master stage master slave C square MOS register. So let us first look at the function, the normal function, then we will see how is it insensitive to the 0 0 and 1 1 overlap. Okay, okay, now let's that in the beginning let's assume that Q is 0. Okay, and let's that D is 1, D is 1 and let us assume that clock is 0, so clock bar becomes 1. Okay, and clock bar is 1, and the clock is 0 actually. So if clock is 0, this M4 is on, clock bar is 1, 1 is applied at the M3, which is an enabling input for an NMOS, for a NMOS. So this is on. Now high voltage, high logic at the gate of PMOS, which turns it off, and similarly this NMOS is also off, not working. So basically this path is not available. It means that this node is disconnected from this node as well as from this node. Okay, so this is a kind of a hanging node which is at high impedance. Okay, and this and these two transistors are available. Okay, now under this condition, when clock is 0, Okay, when clock is 0 and clock bar equals to 1, that makes the master stage in transparent mode and slave stage in hold mode of operation. Okay, so this is in transparent mode, this is in hold mode, right? And depending on the value of d, let's say if d is 1, then this is off, this is not working, and this 1 will make this on. So if d is 1, this is the situation, and node x is connected to ground in this case via this branch, and that will discharge this CL1, and x will eventually become 0. Okay, right? X will actually become 0 under this condition. When clock is 0, clock bar is 1, and D is 0 under this condition. Okay, so it's an inverter. The master stage is acting as an inverter because the output is inverted form of input. Suppose if D was 1 here, 0 here, D was 0 here, that would have made this M2 on and this NMOS off, and in that case the X would have been connected to VDD like this via this because these two transistors were on, and that would have made this X to the value of 1, resulting in the charging of this load capacitance. So when input is 0, output is 1. So again inverter. So behaving like an inverter. Okay. So this will happen under the scenario, and look at here that irrespective of the value of node X. Okay, if node X is 0, that will make this on. Okay, that will make this on and this off. Okay, but it doesn't affect the value of Q because this M8 and M7 are off. So either if M6 is on, in that case Q is again disconnected from this VDD, or if M5 is on, this Q will still be disconnected from the ground. Okay, because M7 and M8 are not available, they are acting as an open circuit. So in this case the Q will retain its previous value. Okay, Q will retain its previous value. So this will say that X will go to D bar, okay, and Q will retain the previous value under this situation. Okay. Now what will happen if clock become once and clock bar is 0? Okay, so this is 1 here, now this is 0, clock bar is 0 and clock is 1. Okay, when clock is 1, that will make this off, clock bar is 0, this is off, this is on, this is on, this is the scene, this is the scenario. X was D bar, so when D was 0, X was D bar, that is X was 1, and let's assume that D still remains at 0. Okay, and Q was 0, the previous value was maintained. Now under this condition, when X is equal to 1, okay, and this 0 will make this turn on and this will be turned off, and the node X is hanging. Now in this condition, master stage will be in hold mode because these two internal transistors are off. Okay, so this node X is not connected to either VDD or ground. This is not connected. The path is not available to either VDD or ground. Okay, so in this scenario, under this condition, master is in hold mode and slave part will be in transparent mode, as both of these two transistors, both of these two internal transistors are on. That will make node Q free to either connect to VDD or ground depending on the value of this input X. Okay, so slave will be in transparent mode, right? Okay, now let's see, because X is 1 here, so that will make this off and this to turn on, and hence Q is connected to ground via this branch, okay, via M7 and M5, and it will become 0. It was already 0, so now also it will remain 0. Okay, so X will maintain its previous value and Q will become 0. Okay, so if suppose if X was 0 here, that would have made Q to 1 via M6 and M8. It would have been connected to VDD. But under this scenario, because this is an inverter, the Q value will be inverted form of X. Okay, so the thing is, for one condition of clock, master stage will be transparent and slave will be in hold mode, and for other condition of clock, the master becomes transparent, and so the master goes into hold mode and slave enters into transparent mode. And these this jumping from transparent to hold, then to transparent, then to hold continues, because the value of clock jumps from 0 to 1, 0 to 1, like this, 0 1 0 1 0 1. Okay, so that will make these modes to ripple like this. Okay, first this is transparent, then this is hold, then this becomes transparent, then this becomes hold, then this becomes transparent, then this becomes hold, like this. It goes on like this. Okay, and the value of D samples into at node X when master is in transparent mode, and the value of node X is sampled to node Y when slave is in transparent mode. Okay, and each of these nodes will hold their previous value if their respective stages are at hold mode of operation. Okay, so this is the normal operation of this master slave C2MOS based register. Okay, this is the normal operation. Okay, now this C2MOS register with clock and clock bar. Clocking is insensitive to overlap. Okay, this is actually insensitive to overlap. This is insensitive to overlap as long as the rise and fall time of the clock edges are sufficiently small. Under this condition, that the rise and fall time of the clock edges should be sufficiently small. Okay, so just to illustrate this, how this C2 or C2MOS register is insensitive to clock skew. Look at this diagram. Look at this diagram. Okay, so what happens when clock and clock bar both becomes 0? That is, what is the condition of this register under 0 0 overlap? let's see when it is facing this 0 0 overlap. Okay, then this M4 is on. Okay, this was off, so that's why this path is not shown here, and this will be available on. Okay, and this path, this NMOS transistor would be off because 0 was coming at its gate, so this path is not shown here. This is open circuit, open. This is also open. Okay, now what happens here is that okay, this is the situation when a 0 0 overlap is occurring to this circuit. Okay, so we see that neither of these stages are in transparent or hold, because one of the transistor is on. Okay, so X has got a chance to be connected to VDD only when this M2 is available. Okay, right. Now when this M2 is available, when a 0 is being provided at its gate, so let's say when D is 0, that makes it on, and the condition of this is not is not affecting, because whatever either this M1 becomes on or off, this is not going to affect the functionality because this is disconnected. Okay, so this makes M2 on, and X may be connected to 1 VDD, so X become 1. Okay, so if X was earlier also 1, then it's not an issue, but if X was 0, then now it has become 1. Okay, so the value of X has changed from 0 to 1, so it's making a transition from 0 to 1 under this condition. Okay, so it is affecting the value of X, this is for sure. Now but we do not want this X to be propagated, this change in the value of X to be propagated to the output Q. This thing we do not want, right? Because if this thing occurs, this value gets propagated to output Q, then it will indicate that the value of Q is changing at the negative edge or the falling edge of the clock signal, which is undesirable. Okay, so that thing has to be avoided. So if X becomes 1, that makes this M6 off, right, and M5 on. So this path is not available, this path is disconnected to Q. So we can say that Q is safe. Q will not be connected to ground or to VDD because M6 is off and this branch is already open circuited. So Q will retain, Q will be equal to QT minus 1, and which is good. Okay, which we wanted actually. But what will happen to Q, to X? X is 1, is making M5 on. Okay, so M5 on will turn, X1 will turn on this M5, right, and the value of X is equal to 1 is retained. Okay, is retained. So there is a change in the value of X from 0 to 1 if the value of input is 0. Okay, but the good thing is that this intermediate output value change is not propagating, is not going to the final output, is not affecting the final output, and that is the thing that we wanted. Okay, now this change in the value of X will affect Q now at the next rising edge of the clock signal. Okay, and at that instant of time the value of X may remain 1 or it may change to 0 depending on the value of D at that instant of time when clock becomes 1 and clock bar becomes 0. Okay, so that's a normal operation, that whatever happens at that rising edge of the clock at that time, the input is sampled to the output. That's a normal operation, that's a normal thing. But the good thing here is that this under this 0 0 overlap condition, okay, the input is not passing to the output directly. input is not bypassing both of these two stages, okay, which had occurred in the previous circuit, but here it is only able to pass only one stage, okay, which is perfectly normal, which will not affect the value of q instantly. Okay, so this is the situation under 0 0 overlap, and when the normal things occur, then at that instant of time, depending on the value of input signal, okay, depending on the value of input signal, q will get affected. That's a completely normal thing, right? And similar things will happen under this 1 1 overlap, okay, 1 1 overlap, right? So look at here, when clock and clock bar both are 1, this is the situation, okay, this is open circuit, not available, 1, this will make this on, this clock is 1, this will make this on, and this is not available, okay, right? So what happens here is that suppose if clock D is 0, that will make this off, and X is not affected, okay, right, and if D is 1, that will make this on, now on, and this path is available to X, and X will go to 0. If it was 1, it will go to 0. If it was 0, it will remain at 0. Okay. So now X may change to a low value depending on the value of D if D is equal to 1. Okay. Now if X is changing its value to 0, that will make this on and this off. So this is the scene for this output node, that this is again disconnected from the high or the low logic. So under this change in X, Q is still able to maintain its previous value. So Q will still be Qt minus 1. Okay, so this is the thing we want, that the input change should not propagate to the final output node. Okay, although it is able to propagate to the next stage, only one stage, but it does not affect the final output. Okay, so it is still safe, the operation is still okay, and the value of Q will get affected only at the next transition of the clock signal, okay, not within this 1 1 overlap time window. Okay, so looking at this operation, we can see that this particular circuit is a good way to deal with the clock skew issue, skew problem, that is when clock and clock bar both are 0, or when clock and clock bar both are 1. Okay, so this can be one solution to deal with the clock skew problem, right? So this is the explanation for the diagram that we had just seen, and simulations have shown that the circuit operates correctly as long as the clock rise time or fall time is smaller than approximately 5 times the propagation delay of the resistor. So try to satisfy this condition, that clock rise time or fall time is to be kept smaller than the 5 times the propagation delay of the resistor. So if this condition is satisfied, then simulation results have shown that the circuit will operate fine, correct. So when you work with this kind of resistor, or when you design this resistor, try to satisfy this condition. Okay, then you can be confident enough that the circuit would function fine properly. Okay. All right, so after looking at uh, these, then there is one more circuit that is known as a dual edge resistor. Dual edge resistor, so that the name clearly tells that the sampling or the capturing of input occurs at both of the clock edges. That is, it occurs at the rising edge as well as at the falling edge. Okay, so when sampling or the capturing of input occurs both, that is at the rising edge and also at the falling edge, then that particular circuit is known as this dual edge type resistors. Okay, and this is the circuit. So look at this circuit. Look at this circuit. This is the first stage. This is the first stage, and this is the second stage. Okay. Again, this is one inverter. This is again one more inverter. This is one more, and this is also one more inverter. So basically, there are 4 inverters for this C2MOS inverters are connected in this fashion. So this is clock bar, this is clock, and its output is connected to the input of this stage, where this is clock bar. Okay, now here is clock bar, clock. So the application of clock signal of this upper part with respect to the lower part is complementary. Okay, so for example, with respect to the location, if this is clock bar, this is clock, this is clock, this is clock bar. Okay, this is clock bar, and this is clock bar, and this is clock. So they are completely dual of each other. Okay, this is one thing, and this is the ground of upper part first stage. This is the ground of upper part second stage, and similarly this is the ground, and here there would be a ground for these 2 stages, and the final output is drawn from the output of the upper stage and the lower stage. They are connected directly, and the common output is being taken from here. Look at here, this is node N1, which is being derived, which is actually, it means that this is connected, this node is connected here, N1 here, and this node N2 is connected here, N2. Okay, so it means that above this M10, which is a PMOS transistor, there is one more PMOS transistor, and then there is a connection to VDD, and below this NMOS transistor there is one more NMOS transistor, and then this ground is present there. Okay, and there would be an application of input signal to these upper and lower transistors, like this is done here. Okay, now let's see the operation of this. So let's see when clock is let's say when clock is 0, that will make clock bar 1. So under this condition, okay, this is 0, clock bar 1, clock 0, clock bar 1, 0, 1, 0, 1. So that will make this M3. Okay, let me change the color. M3 would be off and M2 would be off. Okay, M7 would be on, M6 on. Then here the M10 is on, M9 is on, M13 is off, M12 is off. So basically this particular stage is in hold mode because internal transistors are nearer transistors are off, and this node is neither connected to high or low, right, this node, and this stage is in transparent mode, this stage transparent, and this stage is in hold mode. So also the operation of the upper part would be in complement to the operation of the lower part. Okay, for example, if the upper part second stage is transparent, then at that time the lower part first stage would be transparent. So it will be like diagonally they would be related to each other directly. And if the first stage of upper part is in hold mode, then at the same time, under that condition, the second stage of the lower part would be in hold mode. So this will be the situation under this condition when clock is 0 and clock bar is 1. So let's say if D can be 0 or 1. Okay, so let's say if D is 0, that will make this so irrespective of the value of D, because this is in hold mode, this is not going to change the value of this node X. So here we will get the previous value, that is X t minus 1. Now here look at this node Y. Now Y will change because this is in transparent mode. So if D is 0, Y will be 1, and if D is 1, Y will become 0, because this is basically an inverter stage. Okay, now here look at this, is in transparent mode, so and this is in hold mode. Okay, so this output will be maintaining the previous value. Okay, and this output value may change depending on the value of xt minus 1, because this has now entered into transparent mode. So this will be active here, right? This will be active here, and depending on the value of this node, the value of Q will change finally, because this is still in hanging mode, high impedance, but this will be either connected to VDD or to ground depending on the value of xt minus 1, and that will eventually change the value of Q, the final output. Okay, and when so I can write here that X would be xt minus 1, okay, and Y will change, right? Y will change, and the value of Q will change according to the value of xt minus 1 or X. Okay, so it means that the value of Q is changing. The value of Q is changing. The value of Q is changing under this condition. Okay, now when you go to the other condition, that clock is 1 and the clock bar becomes 0, and you will find that Q will still change here. When you I leave this as an exercise to you to verify these 4 stages functionality, and you will find that Q will still change depending on the value of Y yt minus 1. Okay, depending on the value of yt minus 1. This time this node will be the cause of the change in the value of the final output q. So what I am trying to say here is the value of final output q is changing under both of these conditions, when clock is 0 and clock bar 1, and also when clock is 1 and clock bar is 0. So q is changing under both of these conditions. It means that this implies that q is sampling the input signal at both of the clock transitions, that is at rising and falling edges both. So the action is occurring at both the rising as well as the falling edge. Okay, and that's why it's called as dual edge trigger register, dual edge registers. So here both edges are being taken or utilized to sample the input signal input value through the output node. Okay, so the rate of activity increases 2 times as compared to simple positive edge triggered or negative edge triggered register. Okay, because here the triggering is, if this is a clock signal, if this is a clock signal, then the sampling is occurring at this falling edge, then at this rising edge, then at this falling edge, then at this rising edge. All these edges the sampling is occurring. Earlier we had just capturing of data occurring either at positive edges leaving the negative edge or vice versa. So as compared to those things, here the rate of activity has got doubled. Okay, so it means that with the even with the smaller clock signal, okay, we can still achieve the same functionality with respect to that positive edge triggered or negative edge triggered flip registers, because here the rate of activity has doubled. So even with the 50% with the 50% slower clock signal, the rate of sampling or the rate of activity would be same, or the speed of the circuit would be same as compared to a single simple positive edge triggered or negative edge triggered register. Okay, so this is the advantage here, that you can work with the half the slower clock signal and still achieve the same amount of work, okay, by using these kind of dual edge triggered registers. Okay. So sequential circuits that sample the input on both edges, right? And the advantage of this scheme is that a lower frequency clock, that is half of the original rate, is distributed for the same functional throughput, resulting in power saving in the clock distribution network. So you can save some power in the clock distribution network, okay, because half of the original signal speed would be sufficient enough to achieve the same functional throughput. Okay. So this is the operation, the circuit of dual edge triggered dual edge registers. And because till now we had seen many types of circuits and their operations, and how to analyze those things depending on the value of clock and input. Okay, so I give these topics as an homework to you to read this topic, true single phase clocked resistor, TSPCR, and then in alternative register styles read this pulse resistor and sense amplifier based registers. Okay, these topics can be read from the same book, that is Rabe. Okay, so this whole module 3 till now, I think I have taken most of the portion from this book, Rabi. Okay, John M. Rabi. So I think, and this PDF is available online, so you can download and refer to this book, especially for module 3. Okay, here, and then uh, we will start the next topic in next class. Okay. Okay.